Well, good morning. You're with Michael Crosby. Let's talk a little bit about physics today. Now, we have this thing that I've always had a problem with in my life. I would look at mathematical formulas and some of them I'd go, yeah, that's right. That's dead on. And other times I'd look at a formula and I'd go, just the head says it just doesn't look right. It just doesn't look right. So you have something that what I call now is long formula versus short formula. And different people will say long math versus short math. Yeah, kind of, sort of. You got Einstein, and you have the various equations. You have people talking about the speed of light and how different people interpret what Einstein is saying and trying to understand what Einstein is saying because Einstein says other things. So, at different times. So, some people have a hard time following it. And I'll be honest, I'm not the best with looking at formulas all the time and just it happens and click, 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 everything's going in the head. I see things differently. And a lot of times formulas don't look right to me because they look too simple. Yet, I'll admit, I'm the first guy that wants the cheat formula. If I want the answer, I want to go with the cheat. Got punished in school because I figured out cheat formulas. We were doing huge long division problems and I figured out a really quick cheat. So here we have 4 problems that's supposed to take us 10 minutes apiece, 40 minutes in class. And I finished the whole things and I finished all 4 formulas in 5 minutes. And the teacher's furious. Well, you don't want to show your work. I says, why should I sit there and keep repetitively doing all these zeros and all this other stuff? And they looked at it and they go, all of your answers are correct, but how did you get to them? And they just didn't understand. I told them the short formula cheat because there's a difference between whether it's odd or even. And so you got 2 formulas, one if it's an odd and one if it's an even number. It was a real quick cheat. And eventually some people came out with it. Anyhow, jumping forward, if we're going to travel faster than light, we have a problem because we have all these disagreements in physics. And when you're looking at Einstein's theory is an excellent theory, but things change. As you actually move forward, things change. Einstein does observational experiments. We're going to talk about the train and sound, but you probably know that. So we're not going to talk about that, but I mention it. So if you're going to go to an observation and somebody uses the explanation that if you're going to go to Alpha Centauri 4 light years away and you're going faster than light, that somehow 200 years would pass on the planet. And I'm like, that argument doesn't make any sense from an observational point. Because if I'm looking through a telescope and monitoring you, and it's 4 light years away, and you're traveling at, we'll call it exactly the speed of light, it'd take you 4 years to get there, right? Flat math. We're not accelerating, decelerating, just a quick set as we can here. The problem is, I would be watching you in the telescope for 4 years till you got there. But you have scientists that say, no, that's not what would happen. What would happen is all this time would pass on Earth. Wrong. It wouldn't. That doesn't add up to the same observational items. So, as different people in physics explain things differently, you have to also compare, well, that doesn't go with the train observation thing. If I'm actually watching you and charting you, then there's a problem. Now another problem is when you're looking at the Einstein mathematics here. I'm not going to do any math for you people right now. Maybe later I'll punch it through the AIs, but I'm not going to chalkboard you right now. We're not going to do that. I'm just going to give you a little bit of layman's understanding, so to speak. So when you're talking about again about Einstein's formulas, and it talks about the formula when you get up to light, that all of a sudden you turn into energy. You just convert into energy. The problem with that figure is it's absolutely wrong, but it's absolutely correct. Let me explain. If you are a brick, traveling where the flat side of the brick is directly even with light, as the formula goes, that the more light that hits it, the more energy it's going to get absorbed into the brick. So what you end up is having this brick absorbing all of this energy. Now let's say that this brick was a piece of steel. At a certain point in time, you would have a certain amount of energy hitting it. If you're going directly at the speed of light at 1 mile an hour, that's one statistic. If you're going at 50% the speed of light, you're adding a substantially higher figure of light that is going to be hitting you for each and every second. That's the way it works. If you're traveling at the speed of light, that means that the total measurement of the volume of energy would, for light speed, for one light speed in 1 second, means that you would absorb all of that energy at the same time. So now you look at Einstein's mathematics, the equations are correct. So basically you're going to absorb too much energy if you're traveling through space in a spacecraft. Now you have different shapes for spacecraft. So the optimum understanding here is, I put this out, I don't know how many years ago. I don't think any of it remains on the webs where I did examples. But basically, you have to deal with, there are zones of speed, and when you get to certain zones of speed, guess what happens? Things change. Let me explain a little more. Let's look at the Earth. We have atmosphere, you have aircraft. When you're traveling through atmosphere, we have electrons, we have whatever's in the atmosphere. All those elements, whatever we have elementally, is in the gas. So this is what's going to be striking your aircraft. So we have aerodynamics, which are very important. Let me explain a little more. Aerodynamics are different at different speeds. Things change. For instance, if you're traveling at a certain speed, call it a low speed, aerodynamics are different. The optimum shape for aerodynamics is completely different. If you increase your speed and you start going to a point at certain speeds where you're having a lot of stuff hitting you and hitting your surface areas that are going to cause you problems. One of them is icing. Basically, you're going to freeze. You're going to have this freezing problem at certain speeds. This, of course, is augmented by changes, atmospheric changes. You've got more water in the air, clouds, whatever. It's colder. There's no sun or less sun. So you have to work with all these other factors and figures to understand your icing. So this having been said, there's a lot of people that could explain all these wonderful, insane particulars about this and all the countermeasures, and you're going to put heating in your wings and all this neat stuff to deal with your icing problem. So you have ground icing problems, that's a temperature problem. Then you have icing problems in flight, all the variables with that. So now let's increase the speed. If you're going to increase the speed and go faster and faster, what ends up happening is you have more and more particles, more gas, more electrons, more elements going to be hitting you as you fly. And you get to a certain zone where when you're going, I don't want to use the word too fast, but we'll say too fast. I'll go ahead and use the term. What happens is you start heating up. It starts getting hot. You're absorbing too much. you've got a friction problem. You're absorbing too much of all. You can sit down and do the math and say, well, it's different at different altitudes because you've got a slightly different factor, because the air changes depending upon the altitude. Okay, fine, yes. And you can have a lot of different computations to understand this. So, but obviously, this also has to be known for space travel because of re-entry factor. You got no space. I mean, you have no apparent or noticeable substantial amounts of atmosphere, gas in space. Therefore, it's not a problem. All of a sudden, you go into the atmosphere, and you're on fire. You're in re-entry, and you're on fire. You've got to have a heat shield. You have problems. There, again, you can do the same thing if you have, theoretically, an aircraft that's going to continue to gain more and more speed to where you can be in the atmosphere the total time. And if you increase speed to a certain point, you're going to be on fire. You're going to have so much hitting you. You're going to have the friction problem. It will happen. Mathematically, it's guaranteed it's going to happen. So you come up with people like, okay, we've got new styles of aeronautical variances for all these various stages. You could dumb it down and say you have 3 basic stages: low speed, medium speed, and ultra high spacecraft speed, re-entry type stuff. So now I'm going to tell you that it's very similar when you're in space. It's just that your scale, your zones change. So when you're looking at what you end up having as particles, instead of them being as in the atmosphere, you have light. So if you're traveling at the speed of light and light's coming at you, you have a real different factor. If you're traveling at the speed of light and you're traveling with the light, in other words, you're traveling at the speed of the light away from the sun, versus you're traveling at the speed of light directly towards the sun. These are going to give you different mathematical computations. So, understanding how all of this works and what is the absorption factors, how is this going to work? When you're getting to absorption factors, there's a difference between a brick and considering aerodynamic principles. So once again, the forward move in space is you have to consider aerodynamic principles. So if you look at some of the most modern aircraft that the government's been working on and putting out, you'll notice that they got these things that have these insanely long noses with these very long, they're taking a long time to taper the nose on this craft. This is what you need to do, in theory, at a certain point, to understand what's going to happen if you're going to be traveling at light speed. Because having more surface area to divide out those particles of light will afford you the ability to go faster until you start dealing with your friction problem, with your absorption of energy. So this is why I use the brick versus this. So Einstein's basic equations are short. It's the short equation. If you actually want to study what's going to be happening with elaborate craft actually in outer space, really traveling at the speed of light, beyond the speed of light as well, now you have to bring in a form of looking back at aerodynamics and considering what's there. Because you're going to have changes. These are real mathematical formulas. So now you have the long formula. So that's what's kind of been missing from the Einstein equations, is, we don't have a long formula. We have an oversimplified formula which has an essential correctness. If you're a brick traveling through outer space. So how do we deal with these other principles so we can succeed in traveling at the speed of light. To be able to succeed at it, now we have to consider lessons from aerodynamics. We have to look at the situations, make our readings, do our math, understand how much energy is hitting. Because, by the way, it may not be a constant. Different amounts of light coming in from different angles. There could be multiple sources of light. There can be different frequencies of energy. You can have an imbalance. It may not be a constant. So if you're looking at all these light sources in the galaxy, and now you're going to travel the speed of light, now you're getting serious. If you're really getting serious, now you have to figure out, if I'm traveling the speed of light, how many sources of light are coming at me or coming at from an angle? They're going to have particle presences in space, because you're going to absorb all of this. Now, we can pretend we're a brick and try to understand how we're going to absorb this, or we can pretend that we're this really long, slim nose spacecraft. So, all in all, the long, slim nose gives you a little bit of additional territory. You're gonna just work your butt off doing your mathematics and say, yeah, this is different, but guess what? We still have zones. We're still going to run into these zones where all of a sudden at a certain point, we got a little further, a little faster going, and then all of a sudden we run into the same problem again. Too much energy, and we're basically on fire. We're going to turn to energy. We're just going to turn to energy. So how do you deal with that? So now we can talk about things like magnetism. With magnetism can affect just about anything. Magnetism can affect electrons. You can either repel them or attract them. And magnetism can do the same thing with light. You can repel light or attract it. So I'm sure you'd have a lot of fun looking at all the super collider stuff too in there. So now you have to consider what you can do with magnetism. So let's say that you're going to start playing around with nuclear powered magnets. We're going to start working with metallic diamond components. Okay, we're going to start making these components out of these various materials, and it's going to withstand, like 10,000 degrees, no problem. So maybe we've got this construct of these chemicals that we've come up with for various features. We're using them in everything, from our CPUs, our processors, everything. I've got my designs for years, metallic diamond and multi elements together that in theory will make really great CPUs and really great memory chips. So that's something else I'm fooling with. But if we're going to do supercharged magnets, you have to get serious about it. This is, we're not necessarily at Star Trek yet where we're going to warp space and time, but maybe we're going to go there. Maybe we're going to go to warp. So we have to talk about the next stage up, nuclear powered magnets. So we need a conductive material that has the possibility of, again, surviving in, let's say, 10,000 degree environment. So that means it's got to be metallic diamond, bromide, to this, that, and the other thing. So this construct now becomes your conductive material that you have arranged, and whatever the pattern is you've decided that you want to use. You've got your conduiting factors with a little different conduiting factor, where you might have diamond conduits, which are metallic diamond covered by a different type of diamond. So the energy, again, can in fact flow and still have an insulator. So, maybe you're going to then wrap it with multi-level, and you're going to have this multicolored, and it's going to look like it's a ruby, emerald, something or other. That's a strange looking tube. Okay. Now, working with this as we construct it in new ways, we're talking about, let's just jump forward. Let's get ridiculous. I'm going to get ridiculous on you. It's a bit different, but, for argument purposes, we need to, warp speed forward on this. So we're just going to call it 3D printing, that you're just going to 3D print metallic diamond. So let's say so in theory, we're going to assume you figured it out. So now you have this long nose on your spacecraft, and you're going to do something. You're going to cover how you can project nuclear powered energy in a magnetic, for a nuclear powered magnet. So now all of a sudden you have enormous amounts of energy that can repel light. That means that as the light is approaching the nose of your spacecraft, it's beginning to feel the projection of magnetism, which will protrude. You got another thing at the nose. You're going to do something a little different and push it straight out. Then you're going to have, let's say, these little different angles of magnetism where you're going to control it. Now you might even be controlling it using a different driver mechanism, so that your nuclear electric is just really doing some strange stuff. But you're seriously nuclear powered. You got so much intensity at this point that light comes up to basically strike this sharp cone it's looking at, sharp nose cone, and it's just going to veer off. It's just going to go, whoa! I feel all this magnetic force. So I'm not going to say that you don't eventually going to have a factor that is as though friction, drag. But at first, it should be more like, oops, slide, butter. So yeah, grease. At first, it should be grease. So we're going to use magnetic grease, basically, that's nuclear powered. So if your particles basically are not going to strike the craft, you have just changed everything about the simplistic version of Einstein's equations. Because why? You're removing light from the equation. You're removing E. So how do you compute that? If you're removing E, we just grabbed the rug and said, whoop, we're just going to remove the rug. So what's going to happen here is you got a brand new area. You've just passed this barrier. You can now divert and control light. You've got a grease, whoop, it's just going to slide right over. It's going to be projected away. And you've got your shape designed in the proper contour to get the maximum effect. So yeah, E basically is energy. Atmosphere is atmosphere. So if you're looking at the interchangeability possibilities, you might go insane. But you should see a reasonable symmetry. You can overlay this stuff and look at this and go, wait a minute, okay. So yeah, no, you're basically in space traveling fast. Light is the particle of question. Instead of atmosphere, which is the particle, or actually particles of question, you switch it out. So atmosphere and aerodynamics is like E. In outer space, E might as well be like atmosphere, because we had to use the principles of certain types of higher end aerodynamics to understand how to get to the equation. And now we're cheating on top of that. Now we're taking E and we're controlling E. We're possessing E and we're converting it into magnetism. And then we got all of the other elaborate stuff that I talked about. So you're removing E from the equation for all intents and purposes up to a certain point. Now, there's a trick, or not a trick. There is other factors. How many sources of E do you have? For instance, how much light is coming at you is, if you're traveling directly towards the sun, that's one sun. What if you're traveling almost directly towards two suns, the same size? What if it's three suns, bigger suns? You have to equate all this. So even if you have little or other colored energy sources, balls, okay, all these beautiful colored balls all over the place, and they're emitting energy. So you have to equate how that's going to equate, because the faster you go, the more of it you're going to be intaking, the more of it's going to come into your equation, the more that's going to strike your brick. So the aerodynamics starts giving you a break, but you're still going to have to make some more jumps. Ergo, aerodynamics and ultramagnetic components. So this still isn't enough, by the way. There's mathematics where you still keep going, and what ends up happening is you get to the point where there's so much force in E that your magnetism is becoming outweighed. There's more energy coming at than you have projected equivalent force magnetism. So now you're at another barrier again. So I figured I'd throw that one out there. This is what's going to happen eventually here. Now, so we want to travel back to the practical territory. What's happening when we have our spacecraft where we control nuclear-powered magnetism to basically divert light just enough. So it's like grease. So we got like this invisible magnetic grease. It's grease. And everything's great again. So now we're back into aerodynamics, or at a certain point in time, you're going to get into aquadynamics. In other words, we have aerodynamics, then you got aquadynamics. What's going to happen with all these different types of fluids? Being in fluid, what type of fluid, and this and that. And again, these are real zones. And you will notice symmetry aspects that help you modify your formula creation. At least that's what I seem to have. So this depends on the speed areas. And this is something you can equate. And pretty soon, all the AI computers can be able to equate. You're just going to be able to talk, and it's going to equate, and it's going to invent, it's going to explore, it's going to see the zones, and it'll say, here it is, So whether you're in an E era or E era aqua or E aqua era or whatever you're looking at, this is your reality. Now you need to understand how fast you can go. And say, yeah, you talked about all those equations, how fast can you go? How many times the speed of light? Well, if you're going 68 times the speed of light, then you're going to have 68 more times energy striking your brick, modified by your aerodynamics and modified by your nuclear-powered magnetic factors. So now your equation is something you can work with. You've got all the facts right here. You can now work with it if you want to work with it. Basically, how much can we do about getting serious about it? Okay, that's the front end. That's the front end of the spacecraft. What's the back end look like? What are the engines? How are we doing this? Oh, yes, I did forget a factor. Someone's going to come up and say, Mike, you forgot a factor. Yeah, you do have certain other particles in space. There are some gases in space. So the faster you go, the more you notice these other gases that are, sparse, virtually non-existent. But of course, we could have pockets at any given time that are more. This is a factor for your icing and your cooling understanding. So, yeah, that's real. I'm not going to deny that there aren't factors there. It's going to be something you have to figure out what you're dealing with. Gee, don't make a mistake. You don't want to overheat. So, yeah, you got to cool your components, and you got to figure out what are the zones that could have perceived icing factors as you're pushing away your light. So, yeah, you got another set of equations that's in there so you can keep all your zones happy. So we can go to the back end, and now we're talking about what's our engine physics going to be on this situation. Now, I'm ready to close things down because I wanted to talk about the ability to prove that, in fact, yes, you can move an object faster than light. We're there. Okay, we've done that. We're at a completely different item. So, real quick, let's consider engines. So let's look at particle accelerators. You get particle accelerators, they end up colliding all kinds of stuff, all these different combinations. You get to the point where you're going to have two particles colliding at the speed of light each. So it's actually at collision, they're hitting each other at 2 times the speed of light. Boom. Boom. Then you get a particle that shoots off. And you're creating a new particle. And the particle you're creating is now traveling at 1.5 the speed of light. So if you could, in theory, miniaturize your colliders, definitely nuclear-powered stuff that we just talked about could help do that. And if you have enough space building in the size of your craft, you, in fact, can have the ability to keep colliding particles together to end up with another series of particles that are going at 1.5. So that's 1.5 times the speed of light. So now you would have the ability, in theory, to accumulate those somehow, working your insane mathematics, and now be driving your vessel theoretically near or at 1.5 light. So I'm going to basically fold things up here. Okay, let's add a little bit more. Let's talk about kick plate. So just basic kick plate. You know, the theory in space is that if you put yourself up and you kick applying force, that force is going to be absorbed and it's going to direct things forward. If you have a ring, let's say you have a ring and you have 4 barrels, rifles, that are going to focus at an even spot. Let's call it, 1/4 around. And you're going to fire these bullets, and you've arranged for these bullets to hit this ring that has a taper on it at exactly the same time. So now all this extreme amount of force can basically ricochet. I mean, the bullets will strike the angle, they'll ricochet, but the energy is going to be absorbed into the ring, times 4 projecting it forward. So, there's some, that's raw here. This is just basic raw. So, obviously, in theory, you can push things forward. By the way, all that other stuff no longer applies. All these other factors where people say, oh, that doesn't work, this doesn't, it's endless. So if you're a body in motion that tends to stay in motion and you've hit the speed of light and you're still applying a kick plate or, a force of some type, you're going to keep driving your craft forward. So the difference being here is that if you're a rocket and you're expending fuel, but remember what you're actually riding on is a taper. The reality of a rocket is that the fuel's coming out at a certain speed and it explodes, and part of it's getting affected, caught in this funnel taper. And therefore you're absorbed, the force is hitting it in some kind of an even manner and propelling you forward. So the concept that people are telling you that the speed of the gas and the explosion are a certain amount, and therefore once you get up to a certain speed, you're already traveling that speed, that's all BS. I'll just tell you right now, that's all BS. Don't get confused. When I was a little kid, in the 70s, there's nothing like explaining to somebody and they look at you, how can you be like an 8-year-old or 10-year-old saying that, oh no, it doesn't work that way, it can't work that way. So you get a headache listening to your teachers because you already understand things about light and energy beyond them. You see, that's what you get for being born with an extreme high IQ and going to the school system. So, in reality, you have to remember your BS points because the reality is it's still going to apply. The question is, how do you make this efficient? How do you make an efficient way of continuously putting force so that you can accumulate? Because, by the way, there's also differences because applying force at a dead stop will move you the first 10 feet at a certain rate. But the same amount of force reapplied again, the bullet factor, for instance, you fire the 4 even bullets. That's going to happen on the next 10 feet is different because you're already a body that's in the tendency of being in motion. Therefore, basically, the understanding of static weight is different. So what happens in the next 10 feet is that there's going to be this bit of a change. The same amount of force is not going to propel it 10 feet. It's going to propel it more than 10 feet. So its relationship is unto itself as far as the spacecraft goes. You've now placed yourself, if you can imagine, in a form of an envelope. You're in a magnetic envelope and you've eliminated E. So, now you can talk about all those other little neat things, inertia and all this other stuff. And yeah, you still have to pay attention to the laws of acceleration. Because if you accelerate too many G's, you'll just turn yourself into mush. But there is an equalization, that factor that some people don't mention, that the same amount of force on a rocket eventually equalizes. The passengers inside eventually get used to you end up with a form of equalization. And then you're like, oh, it's okay. Now I'm traveling 25,000 miles an hour, but I'm floating and there's, not much happening. So this is what's going to continuously happening. But the immediate acceleration beyond that, adding a different curve, is what you have to keep dealing with in your mathematics. So how much can you continually accelerate? Comfortably. So once you get past that, now you get the mathematics that you can sit there and keep accelerating again and again and again, and you're going past light speed, way past light speed. You're basically going to get up to what I believe are certain different zones. You got all these different zones for different reasons. There's different factors of why you got to weigh how the energy affects you. What is your cross consciousness to everything else. And I mean, you could even do quantum relationship. If you want to do a bunch of ridiculous mathematics. But because then that's times, all these other parts. It's insane. Okay, so I want to say that the difference in fuel ability consumption to be still cost effective is basically in our hands right now, that we could go 68 times the speed of light if we really wanted to. 4 times the speed of light, piece of cake. We could do this. So going to Alpha Centauri is something we could probably do in 6 months or less. When you're talking about let's go 68 times the speed of light, how fast are you going to be going? I mean, how far do you want to go? Because you can spend all this time accelerating and then a whole bunch of time decelerating. So you have to figure these things out. So, of course, now you're introducing a different engine mechanism to also be there someplace in the aircraft or in the front of the aircraft, multi places in the aircraft or spacecraft, to be able to control deceleration. If you still need the point, you still need this pointed magnetic thing so you don't fry. You can't just turn around and say, yeah, we'll just fire the engines the other way. No, you have too much energy coming at you. You have to keep your magnetic shield going. So the reality is if we really want to do it, is that making a 4X light engine situation, we can do this. 8X. There's going to be a bunch of people out there, by the way, they're going to argue with me. Well, I'm right, and y'all's wrong. That's just all there is to it. And you're going to have somebody say, national security, man. We lied about water being on the moon because we didn't want a super space moon race. Whatever. Okay, maybe then, yeah, whatever. Okay. So now these calculations mean, wow, one country can send out more Millennium ships than anybody else and take over the galaxy in front of everybody else. And then the future, 10,000 years from now, will have all of the habitable planets and all the good mining areas controlled and owned by somebody. Maybe it's you or not, right? Okay. So basically that concludes the little talk to let you understand a little bit about long mathematical theory for dealing with Einstein's formulas concerning space travel and the speed of light. Because the factors involving these items to be able to allow you to do it, we just changed all of them. So a lot of things are seriously in questions. If we're going to talk about spin factor rotation and other factors involving your personal quantum life clock, that's another series of arguments that has to be dealt with. But I already covered the reality that from the observational standpoint, there's no logic to say, yeah, we're traveling at the speed of light. It's 4 years to Alpha Centauri. It'll take us 4 years to get there, but 200 years is going to pass on Earth. That doesn't work from the observer's standpoint. Going, no, I'm looking at you, and I've been tracking you along in 4 years, and you're on a schedule, and BS. That argument does not work, does it? Their argument doesn't work there because it doesn't meet the observational understanding. So, we can do space travel. We do have these other zones that we'll have to attend to. But most importantly, a new frontier's opened up. We have various asteroids full of very interesting minerals. We need to make plans to mine them immediately because we can figure out a way to mine the gold cheaply, robotically. And that'll change the entire monetary system. It will add solidity. Okay, I'm getting tired. I got to pass out. That's what happens when you wake up too early and you don't get enough sleep. Have a good day.